I'll start. And so this is the title. And I'll start with a quote from Wikipedia, which is one of my favorite pages about the ADE classification. And this page is becoming longer and longer over the years. And at some point in the pages, there are these sentences. So one is that there are deep connection, oops, that's what I meant, deep connection between these objects and hinted at by the classification. And there is a list of objects. One is the ADE linking diagrams, which is ADEs of the titles, Lie algebras, discrete subgroup of SEC, the binary polyhedral groups and the Platonic solids, Duval surface singularities, elliptic surface, Mackay correspondence, Hugo's and Expero that, and ... and the list goes on. Then there was a question in 1976 by Arnold, which is to find a common origin of all these ADE classification theorems and to substitute this a priori proofs to a posteriori verification of the parallelism of the classification. And then if one goes further down on the Wikipedia, it goes like this. There is something in red. You see, this is red quoted from Wikipedia with statement citation needed. And the statement says there are deep connections between these objects, and some of these connections can be understood via string theory. And then it says citation needed. The plan of the talk is to review some of the points that I stated before, some of these objects, and finish the talk with a hint of this part, or the citation needed. So what's the influence and what's the impact of string theory in understanding and making sense, putting together, really stringing together, pun intended, all of these questions. And prominent is the work of Grothendieck and Brieskorn, which I'll talk about it towards the end of the day, and what I like to call a Grothendieck-Brieskorn program. And I'll talk about providing evidence via complex algebraic threefolds, and I'll talk about some applications. So this is the plan of the talk. That's the plan of the talk. And I'll start with Klein. So following Klein is, he made the statements, these are my picture, of rotational symmetries. These are rotational symmetries of the extended Platonic solid. Extended because we start from an n-regular polygon. This is an n-regular polygon, and the symmetry are z over nz. There are n of them. And then what we call the dihedron, which is a double regular polygon, so like two polygons on top of one another, and calls them dn, and there are two n of them. And then the symmetry of a tetrahedron, rotational symmetry of a tetrahedron, A4, the alternating groups on 4 letters, there are 12 of them. And then the groups of the cube and the icosahedron. The cube is dual to the octahedral, as I tried to put it here in the picture. So we get the octahedron by putting a dot in the middle of each of the faces of the cube and joining the dots. And 24 of them here. This is S4, symmetric group on 4 letter, and then A5 for the icosahedron. And I did not dare to draw it, but I think we can all imagine it, or if not, find it on Wikipedia. Now, note, so what's a note? This finite groups, which is F bar, the rotations of S3, these are finite subgroups. And in algebra, we learn, or some other course, that there is a 2-to-1 cover, which is called the spin map of this SO3. This cover is the complex group SU2C, which is the group of 2x2 matrix, this special unitary group with complex coefficients. And this is a 2-to-1 cover. So we're taking our finite group F bar, so they're the inverse image, we call it F. And for example, SU2 here, I wrote down the definition is the special unitary matrices, which are determinant equal 1 and A inverse equal A transpose conjugate. So the theorem of Klein is the finite subgroup of SU CR up to conjugation exactly there are these, so there is a finite list, and except for the first one and n odd, all the others, they are the 2-to-1 cover of the rotational symmetries of this extended Platonic solid. And these are the names, again, following Klein, and this again is their order. So that's the theorem of Klein. Example, so an example, so this is the first one, this is the first one here, this is the group Z over NZ, this is generated by these two elements, matrices, theta, where zeta is n root of the unity. This is a matrix, and this is a group, this is a generator, and this is an example, is a generator of the other group, the dihedral group, the N, and this is two generator. One is the same generator of the previous one, and then there is another generator, which is this matrix here. So going back to the Wikipedia page, I'm putting in orange with a little here check what we did. So using the theorem of Klein, I described the discrete subgroup of SU2C, and then relating them with the binary polyhedral groups and the Platonic solids. So that's one part. Now, next, Duval singularities, or rational double points, and how do they appear? So I'm going back to the a very particular case of this example that we got here. So for n equal 2, we have the root of the second root of unity. So F, this is the group, and this F acts on C2. And acts on C2 in this way, so just a matrix multiplication. And this is a negative, U goes in minus U, V in minus V, and we have invariance polynomials. And the invariant polynomials are the squares in U and V and their product. So the symmetric polynomial of degree 2 in two variables. And they have a relation between them. And if I give a name X, Y, and Z, then the relations is that XY is equal Z squared. So we can write this as a quotient of this ring. And we can consider the zero locus, so of this ideal. And this is a surface. And this is a surface. Oops, this I made a mistake. C2 over F. This is a surface, and this is a surface I associated to this group F. Now, S is familiar to us from high school. This is a quadric cone, and this is the picture. And the quadricone is singular at the red dot here that we have. And we can see verify that it's singular because all the partial derivatives are equal to 0 at the origin. But we know that this is a particular surface with a particular singularities. And the singularity has a property that if we get the volume form on C2, so D2, du, wedge dv, let's say, where these are the coordinates where we started with on C2, and then we take the quotient, then this volume form survives in the quotient. Although the quotient is singular, and in principle, we can define volume forms only on a smooth part of this object, then we have that the volume form goes to the quotient. And this is what in algebraic geometry is called the canonical divisor. So I put it in quotation mark, KX. Now, Duval, we're moving forward from Platonic, so big jump to Klein, and then from Klein, a little bit of a temporary jump up to Duval to 1934, and Duval wrote a paper whose title is exactly on the singularity which do not affect adjunction. And the statement result is that these type of singularities, so every time we take a C2 mod an action of this finite groups, the one described by Klein in SU2C, these are all the isolated surface singularities which do not affect adjunction. What are the means? So what I'm going to do next is to describe some of the properties uncovered by Duval's about these singularities, and explain what it means by that the singularities do not affect adjunction. Now, theorem, before doing that, there is the theorem. This is the theorem by the Klein-Duval singularities, is that as we did in the particular case for n equal 1, and so the action of the group Z over 2Z, the invariant polynomials of C2 over F, oh, this is really disruptive, define singular surfaces in C3, and they have explicit equation, and we have two infinite series, the AN and the DN, defined by these equations, and then three isolated ones, the E, E6, E6, E7, and E8, and this they have the equation. And the partial derivative all vanishes at the origin, which is the singular point of these surfaces. So we already done Platonic solids in discrete groups, and we reviewed the result of Duval that about the singularities, surface singularities, or rational double points, double because they all have multiplicity 2. And then I want to explain the statement, the result of Duval, that these are the singularities which do not affect adjunction. And what does it mean? So it's possible to define intersections on these surfaces. So one way to say is that these are Q factorial. It's possible to define the volumes, as we saw before, and which I call also in algebraic geometry, this is called the canonical class of the canonical divisor K of X. And one can resolve of deform the singularities, and Duval statement in modern language is that the canonical class is preserved in the resolution. And the singularities are all the surface singularities which have this property. So I want to ask if there are questions right now. Before the next part, where we're going to talk about resolution and deformation, because I made a statement that one can resolve or deform the singularities. So, okay, so a few words about resolution and deformation. And I'll start again with an example, with a concrete example, one dimension lower. So we're talking about a curve. So a singular curve, this is an example of a singular curve. I drew a picture, and the red dot is again the singular point. This is the curve. And we can see that it's singular by taking again the partial derivative. And it's a statement that this curve C can be rationally parameterized. So what does it mean that can be rationally parameterized? Well, we can fix the origin, and we can take all the lines through the origin and then consider the intersection of the line with the curve and associate essentially to the slope of the curve to the origin, the intersection with the curve. So one can do it explicitly. So I'm taking U, this is really the slope of the curve through the origin, and I'm parameterizing the point X and Y. X and Y are points in the curve C in the plane, and parameterize it this way. So this is a parameterization and rational because it's done by U in C. And the claim is that this parameterization gives a resolution of the singular curve. So what does it mean if I'm taking geometrically, if we're taking at all the slopes, we have a unique point, but when I get at the point here, I get to the point in two ways, right, with the two slopes over here. So if I'm associating the slope, it depends on which sides we are arriving. To this point here, we are associating 2 points in the parameterization. These both red points go to the red singular point. So we have taken apart the singular point, and this is called the resolution. It's called a birational resolution because if I remove this point, we remove this point, or these are 2 points here, the rest of the curves are isomorphic. So nothing has happened outside this point. So on open, dense sets, the two curves stays the same. And this is what's the principle of birational resolution. So now, if we want to do projective geometry and we are over the complex, we can compactify C to P1. So it means we compactify the complex line to P1, which is an S2, the curve to the closure, and topologically, so we are, instead of getting algebraic curves, we get a Riemann surface, which is a real orientable surface, and it looks like this. While the singular one looks like this, so it's a pinch torus, the resolution looks like what's happening really means pulling apart the points. So this is the picture here. that we obtain. So we take the singular point here and we pull apart to this other point. So this is what's called a birational resolution. It's a theorem, and this was known in the 1800s. I don't know by whom, but was definitely known by the 1800s, by that resolution of curve exists. A resolution of curve exists. And we can do something else also. We can, given the same curve that we had before, we can deform it. So by deform it or smooth it means we can add a parameter, say different than 0, and the result is that we kind of pull apart, we sort of pull apart here the origin to this other curve and to this other smooth curve. And if we consider the Riemann surface associated to this curve, this is a result of Weierstrass, that this is topologically actually a torus. So what we have done, the singularity, if this was the singular curve, we have resolved it. So we mean we pulled apart the 2 points, or we also we have deformed it. And by deform it, it really means we are kind of filled up like this neighborhood of the singular point and made a torus. So there was like a circle here. It's like virtually if we had a circle, which is called really the vanishing cycles on the torus, and we contracted it down to a point. So this operation are the smoothing and the deformation, the resolution and the deformation. And these two, as Riemann surfaces, are topologically different. So these are completely different. When we take something singular, these two are isomorphic on open set, and this one is totally different, although the equation somewhat seems similar. So I'm talking about this because the singularities, the Klein-Duval singularities have a very interesting property. So that both the resolution and the deformation of these singularities are locally isomorphic. Diffeomorphic, actually. Diffeomorphic. I made a mistake here. So an example, and again, I'm taking a picture. And again, this, I'm taking two singularities. One is this one here. The other one is the dihedral D4 that I wrote before. That's the singularities. And the resolution, the deformation, which is the easier to see geometrically, we add again a parameter t. And so what happened, this is a real picture, to this point here, to the singular point, we fill in an S1. And the D4 that looks like this, if we fill in the vanishing cycle, so we smooth it, adding a parameter t, we get these pictures, and we get 4 vanishing cycles. And the claim is the property of the singularities is the deformation and the resolutions are exactly the same pictures. So if these are the vanishing cycle that can then shrink to this one, these are also the real picture of the exceptional curves, which they play the roles of 2 points here in the resolution of the curves, which they can send down, shrink down to a point. So same picture in the resolutions and the deformation. Now, theorem, and this is a theorem, resolution of surfaces exist. And for the case of characteristic zeros, so certainly true for the complex number, which the one that we're considering in this talk, they were proved first, I think, by De Pezzo in 1892, and then by Beppo Levi, Chisini, who was here a student in Bologna, Albanese, Jung, and then all the books, all the historical books, they do say that the first algebraic proof was given correct, consistent algebraic airtight proof was given by Walker in 1935 and Zariski in 1939. So these proofs here are analytic. They don't use differential algebraic geometry. They use hard analysis. So in fact, I was surprised because I studied Beppo-Levi in analysis, not in algebraic geometry, but turns out they gave one of the proof of the analytic proof. So anyway, the singularity exists. And now we can go back to the statements of Duval and see what it means that these are all the isolated surface singularities which do not affect the junction. So what's a junction? So I decided I will give a proof. And so this is the proof for the talk. This is the only proof that I'm going to do. And this is about the statement. Then the singularity C2 mod the involution, which we saw before, does not affect a junction. Now, what's a junction? So junctions, we have that if we have an object, a variety, and an hypersurface, and let's say this is of dimension 3, like C3, and Y is our surface of dimension 2, then I can compute the volume. Then I can write it in this way as the canonical class as the volume of the total space restricted to the class of Y plus the class of Y and restricted to Y. Now, I learned this from reading Shafarevich's book on algebraic geometry, but the proof is really writing like the volume form, du wedge dv wedge dw in the ambient space, and I'm restricting it to the surface doing the calculation using non-singularity. And this formula comes out. This is the adjunction formula. Now, I wrote it this way instead of volume because it's just a little easier. So this is a volume form and the canonical class. Now, if we have now a resolution of this surface, which is a surface in C3, and the result surface, so this object the result surfaces lived in another three-dimensional object, which is called the blow-up at C3, and the adjunction says exactly this. Now we're going to apply it to the pair ambient space here, surface here, and ambient space here, surface there. And by doing the calculation, really, what does it mean to do the resolution, to do this pulling apart the point that I described for the curve, doing the same for the surface, by doing the calculation, turns out because the volume class on the ambient space has a 2 over E, and E is the exceptional divisor. That cycle, then we add the circle in this picture, and because the strict transform of the surface is the pullback of the equation exactly that we have here, minus twice, minus 2, or multiplicity 2, again, over the same locus, over the exceptional locus, then when we add them, when we pull together, what do we have? We have exactly the pullback of the resolution of the volume of the singular surface is exactly the volume of the result surface. And that's what Duval meant by the statement that these singularities do not affect the junction. So this is reasonably easy to prove. This direction verified one by one, the other direction I'm not doing. So, and this in algebraic geometries, these are example of canonical singularities. So Miles Reeves gives the names of the singularities, gave the name of canonical singularities in the 80s, I guess, maybe even late 70s. So question, comment at this point? So, well, another something that comes in is the Miller number of an isolated singularities, and turns out here that the Miller number is that by deforming the singularities, like we see here, we have the vanishing cycles are a bouquet of spheres, and here the bouquet of spheres is exactly as we see here. It is a bouquet of S1, really, and their number is exactly the numbers of these vanishing cycles of exceptional divisor, and they can also be computed algebraic like this. Now, another thing we can do, we can consider the dual diagram of cycles and of this exception of the vanishing and exceptional cycles. What do we mean by dual diagram? So it means that for every exceptional cycle, we put a point and we put a line between the two of them if they intersect. So in this case, we only have one point. In this case, the dual diagram will be this one. And now a theorem, and Klein, Duval, and then Artin more recently, is that the resolution of the Klein-Duval singularities have, or the deformation equivalent of Klein-Duval singularities, because we've seen that they are locally diffeomorphic. Then the dual diagrams are these diagrams marked with the letter A, D, and E6, and E7, and E8. So we have 2 infinite series and 3 exceptional cases. So E for exception. So the dual diagram. Now what we have, going back to the page of Wikipedia, we have also seen how the AD linking diagram come into this picture. So now Lie algebras. So these this diagram, the dual diagram, are the linking diagram of Lie algebras. And these are the Lie algebras. So AN, this is SUN, and this is SON. And these are the exceptional algebras, the algebra E6, E7, and E8. I'm not reviewing the definition now. We'll see it later in the examples. Now, how does it work? And so this is the example. If SU2 is the special unitary Lie group, then little SU2 is Lie algebra, which is the tangent space at the origin. So the origin is the identity in this, the identity of SU2. These are the matrices which have this form. So anti-Hermitian matrices that are traceless. So anti-Hermitian matrices which are traceless. So this gives traceless. And this is the condition of anti-Hermitian, so conjugate transpose. These are the diagonal matrices. So, and this is called H. And H, these are matrix groups. And this is the explicit description of the Cartan subalgebra of the Lie algebra. Its dimension, which we see in this case is clearly 1, is the rank of the group. And a property is that the Cartan has a lattice substructure, so an inner product. And with inner product, we can associate intersection. And again, we can associate to each element a dot, and we can do a dual diagram, and again put a line connecting two dots if the two dots intersect. And a theorem, the theorem is that the linking diagrams determine the Lie algebra. So, claim, going back to Wikipedia, we have visited all the main points which I stated at the beginning of the seminar. So the question is it only a parallelism? And that's a question asked by Arnold. Or is it a coincidence? Or there is something more? And so I'm going back in time again. In the realm of coincidences, Kepler, and it was not really his doing because it was not totally at fault, because he relied on observation given by Tycho Brahe, and Brahe did not want to give him all this observation, but only partially the observation that he had. And so based on this partial data that he had, Kepler made an observation, let's say a conjecture. The planet, that's a picture, made a model of it. And this is the Mysterium Cosmographicum. That the planets, at least the planets known at the time, so there were 6 of them, could be modeled, or rather their orbit could be structured one on the other, like in this picture here, following the model of the Platonic solids. And he realized, Kepler, then the number were a little bit off, but he claimed there could have been a computational error. So we know now that this is, of course, not correspondence between the Platonic solids and the way the orbits are one encased, one in the other. So this is a coincidence, and as a warning that we have to be careful to see if we're talking about really coincidence or if there's something behind. And then in the 70s, came in Grothendieck and Briscoe. Grothendieck a conjecture, Briscoe proved it, and Slotowitz extended it later for the groups which are not simply laced. So from ADE to the BCFG. And what's their statement? The statement is that if we start, this is the statement of Grothendieck and Briscoe, not as Slotowitz. So if we start with a group, a complex group, this time this is a complex group of type ADE, then through representation theory, and I write it here, it's possible to find inside this group variety X and S, which are really determined by the group and their representation. S is a surface, S is a slice, so the character, so the traces of this matrices determine a surface inside this group, and this surface really has the isolated Duval singularity of type G. So the statement is, we start with a ADE linking diagram. The linking diagram correspond to a Lie group, Lie algebra, we take the complex form of the group, study the representation, and cleverly using the characters, so the traces inside this, we can find a slice, a surface, which is exactly the singularities, the ADE's type of singularities where we started with. I find the result absolutely amazing. And I want to illustrate it for the case when G is the group SU2, SU2C. So the group Z is again the involution Z over 2Z. The compact part is SL2C, the special linear group. So it means the 2 by 2 matrices with determinant equal 1. The characters are the trace, and the surface is given by the inverse image of the identity. So S is this time, S is the point, this surface, and is given like this. So I want to look at the inverse image of the trace has to be the identity. So all the matrices on the diagonal, I have to write it this way, 1 plus alpha and 1 plus delta, with the condition that alpha plus delta is equal to 0. This goes down to the identity. And then we want to have that the determinant is equal to 1. And because I already imposed this condition, the determinant equal to 1 becomes this other condition. So applying the theorem of Grothendieck and Brieskorn, one finds that S is the locus in SL2C, which satisfies this property. And then by combining these two equations, we get this equation. And this is exactly the Duval singularity associated of the equation that I wrote before, associated to C2 mod F, where F is Z over 2Z. So this says it is not a coincidence. So there is something between, something deep between, is not a parallelism, but there is something deep. So it is between the, given a Lie algebra and a linking diagram, we can recover the Duval singularity. So the Duval singularity sits inside the algebra in a natural way. And then slowly generalize on the non-simply laced groups, which are the groups that we obtain by an outer automorphism of the AD of the linking diagram. This is a local picture. And the last 10 minutes of the talk, I want to talk about the citation needed, about the prediction of string theory, about the correspondence between algebra representations and geometry. So I'm going to stop here and take a little break and ask if there are questions before I go forward. So the last part is that gauge theory, quantum field theory, suggests a correspondence between Lie algebra, actually U1, so also abelian algebra, not only Lie algebra, their representation, and the geometry of smooth Calabi-Yau varieties, which are of a certain type, elliptically fibered. And this is a global picture, is a picture which is together, which is not local only, like in the Grothendieck breeze continuum, but is global. So it refers to all varieties. And in reality, what we learned by studying the physics is that the correspondence goes between, from the geometry of varieties and elliptically fibers, one can only always find the Lie algebra and the representation. And the Calabi-Yau condition, which I'm going to define next, talks also about the other direction. So it's like local to global principle, how all these singularities ties up together. Grothendieck and Briscoe results talk about singularities and Lie algebra. String theory goes beyond and makes it from local to a global picture and adds representation, not only Lie algebras and the representation. And what we learn is that in the Calabi-Yau case, given the algebras and representation, they constrained the geometry of the Calabi-Yau. So why is that? The constraint is what the physics call the anomaly cancellation formula in dimension 3. And that's a constraint which brings together all the local information. And that's somewhat the missing piece from the picture that we had in the 70s from Briscoe and Grothendieck. So this is a program, this is something that I've been working for decades right now, with various collaborators, trying to determine in mathematics method which associate to the elliptic vibration, associate mathematics to elliptic vibration, algebras and their representation, and vice versa. And prove properties. Now, I want to conclude also, because we're getting towards the end also, again with an example, a very concrete example to see mathematically how this works in a very concrete example. So if you're tuned off a little bit, it's a good time to come back in. So concrete example, how we go from a local to a global picture in a way that we can draw pictures, and which is a two-dimensional case again of surfaces. I'll go back and describe the role of the physics and the conjectures. Let's go back to the math. So this is an elliptic curve. This is a complex C. This is C mod a lattice. This is a torus. That's the one I drew before, and we'll call it E. And the theorem of Weierstrass tells us that this object can be written as a curve in the plane. And this is like the curve, the deformed curve that I wrote before. That's the equation. And we can construct something which is called a Kummer surface. So we take a product of two elliptic curves like this, and we can do an involution, sending x and y in minus x minus y, exactly like we did before. But instead of doing locally, now we do it on something compact, on a torus. And we get a surface, which is called the Kummer surface. This is singular and has exactly 16 A1 singularities, which I drew in here in this picture, the red dots, and the A1 singularities are exactly the one that we've been looking at all evening. X squared plus y squared equal z squared, the singularity of the cones. And this is a picture. The claim is that the projection EE on one of the factor induces also a projection on the quotient. and this is this one. And on the quotient of the elliptic curves, that gives a P1. And again, here we have the Kummer surface. And outside of the 4 fixed points of the involution, which I drew them in red, where the fibers are again double lines or P1, then outside that, the general fiber is the elliptic curve, because when we don't have a fixed point, the fiber is exactly just like this, an elliptic curve, except it will move around. So these are A1, these are the Duval singularities, A1, and we can resolve them like we did before by adding, for each of them, adding one of this exceptional cycle. One of them, we had a dot. So we had these pictures, and this is the model, what's called an elliptic fibration with a section. Section because the copy of the P1 of the base that we had here, we can take it back, and I drew them here. So there is a section that goes through. The discriminant are these points, that's a technical language, and this is exactly a model, a definition of an elliptic fibration. The singular fiber are exactly around these points. There is a lot can be said about elliptic fibration. They're unreasonably ubiquitous, both in mathematics and in string theory. So in mathematics, it's a classification issue. In birational geometry, string theory comes out from many searches, computer searches, even recently now with artificial intelligence, to discover, to prove that statistically many of these Calabi-Yau varieties have elliptic fibration. So now Kummer, where we are, so we look at what we have done. So we have added at the singular point, we have added, instead of doing a circle, now I just added a line. We can do the dual diagram, and the claim is that if we forget the component which intersect the section for each fiber, now we got a dual diagram of D4, which is the one that we constructed parallel to the U1. Claim is we can get in this diagram, we can go back down to the singular D4, and we do that because going down on the singular D4, we have that the resulting surface has an equation that we can write it as hypersurface, exactly like Weierstrass did for the elliptic curve. And this is called the Weierstrass model. This Weierstrass model, the surface has 4 D4 singularities. Now, this is not a coincidence because D4, we associated B4 with now Grothendieck-Briescourt locally. We can associate each of them to the Lie algebra SO8. And in physics, so the physics is that F theory compactified on X Calabi-Yau is dual to F theory compactified. What does it mean? On B, that's a language. This is a string theory compactified, in our case of the Kummer, on P1 with branes. And the branes supported the discriminant locus. And what are the branes? The branes are branes associated to the Lie algebra SO8, to the gauge Lie algebra. So that's how the gauge theory, the quantum field theory, comes into a web of duality. I'm not giving a definition, formal definition of a Calabi-Yau. I'm just stopping to say that the Kummer is a two-dimensional version of a Calabi-Yau. So the Kummer is a two-dimensional Calabi-Yau and is called also AK3 surface. And through a web of duality, of physics dualities, heterotic theory, M theory to be back to F theory on this Calabi-Yau, let's say on this Kummer, tracing back the property, the physics has been predicted since the mid-90s, relations, Weber duality relations between this Lie algebra and actually also the Mordevai group of section and the torsions of this geometry. So the program is, and what I've been, the claim is that there is a correspondence. The program, what I've been trying to study, what I've been studying for decades now, is to analyze and make a program. It explicits this correspondence between their algebra and their representation and the elliptically fiber variety X to B in particular, where X is a Calabi-Yau triple, and give geometric origins of the algebra and the representation, and state and prove formula in mathematics which correspond to the constraints which we get in physics as a local to global principle. And this is a program which I've done over the years with many collaborators at this point. And I want to conclude to say what's involved. And what's involved involves everything else that I mentioned this evening from the very beginning. Well, actually, something this I've not mentioned is non-degenerate pairing on X. So Poincare duality. Poincare duality might not hold on variety with singularities. So one has to be careful on this one. Morsifications, which means really taking, in some way, deforming the singularities and looking at vanishing cycles. From algebra, so this is more topology, and that's a method we use with string junctions. Versal deformation, algebraic geometry, Milnor numbers, again, topology and deformation. And then lately, enumerative geometry, in particular the Kopa-Kummer-Vafa invariance, and a lot of representation theory, which representation theory, in particular branching formula, which tell us how to get to the representations, not only the Lie algebra and the representations. And there are corollaries and various results that we can prove. And but I think I'll stop here because it's 10 o'clock my time. So thank you for your time.